Alright, this is the last video for section 12.1. We've talked about two types of surfaces that can be defined by our multivariable functions. We've talked about the planes, which are just the ones where all the variables are linear, or to the first power. We talked about cylinders, which is an equation that only contains two of the three variables. And last but not least, we're going to talk about quadric surfaces. Now these three types are specific types, planes, cylinders, quadric surfaces, but there are many, many other graphs of three-dimensional surfaces that we've not really even scratched the surface of, no pun intended there. And of course Maple will help us out in general, and we're going to talk a little bit more about that as we go on here with this section. So first of all, the definition of a quadric surface is it's a graph of an equation in this form. And what I want you to notice here is the degree of the x, y, and z is degree 2. So it's kind of like quadratic in a way. It's second degree. Even these are really second degree terms, right? Two first degree terms multiplied together would be second degree. They can also have first degree terms, that's fine, constant term. But ultimately, the highest degree of each term can't be any more than 2. The simplest form would just look like this, and we're going to look at these first, and then we'll also look a little bit at shifts of that form. You have on the next page a table, looks something like this. You'll note that this is also in your formulas packet that you'll be able to use come midterm time. And we're going to be basing our graphs here on the equations and the graphs that are in the sheet, so I'll be referring to this quite a bit. Couple of quick little pointers and then we'll get started. When we graph these things, it says complete the square if necessary to identify shifts. We'll see a couple of examples of that. Using that table we just talked about, identify the type of surface and the orientation. Again, I'll make a little bit more note of that as we do some examples. And then finally, to a limited extent, I'll use some traces to help me graph. Keep in mind that the traces are the intersection of the surface with the coordinate planes. So what that means is the xy trace would be the intersection of the surface with the xy plane, or in other words, with z equals 0, right? That's the equation of the xy plane. Xz trace is the intersection with the xz plane, which has the equation y equals 0. And finally, for the yz plane, we'd be setting x equal to 0. I won't always do the traces with all three planes, but to a limited extent, I'll use traces to help me graph. And you'll see all of that as we start popping through some examples. So let's do that. All right, as it says, identify each quadric surface. So I want to actually tell what the name of it is. Orientation, again, you'll see that as soon as we start doing some examples, and then if there are any shifts, we'll identify them. Sketch, using traces to help as needed. We're going to do some sketches by hand, but I'll also be referring to some Maple graphs at the same time. All right, so as I look at this first one, I'm going to notice that in my quadric surface, all of these squared terms, 2 of them are positive and 1 is negative. Looking at my list, I'm kind of interested in this one right here, the hyperboloid of one sheet. Notice the x and y squared terms are positive and the z squared terms negative. So it seems like a pretty good fit for what I have. I will note, however, that the right-hand side is 1. So to get it to be a really good match, I'm going to go ahead and say, let's just divide everything both sides by 16. Trying to create that 1 over here on the right-hand side. So I'd have x squared over 16 plus y squared over 16 minus z squared over 4 equals 1. And now that's a perfect match for this hyperboloid of one sheet. So my name, hyperboloid of one sheet. All right, let's see here. Next thing I need to do is try to figure out how I'm going to graph this thing. And in order to do that, I'm going to look at one specific trace. I'm going to look at the XY trace. Right. That means I'm going to set z equal to 0. And if I do that, I'll get x squared over 16 plus y squared over 16. The z will become 0, so that'll just equal 1. Sorry, my screen's freezing a little bit. My apologies. Go back over that one more time. Again, that trace would have z equal to 0. So when I plug the 0 in for the z right there, I just end up with that equation. All right. If I multiplied back the 16, that would say x squared plus y squared equals 16, which is just a circle of radius 4 in the xy plane. So I'm going to start with that. In the xy plane, I'm going to try and draw a circle of radius 4. And I'm going to kind of make a solid line in front, and this is eventually going to be hidden, so I'm going to draw it as a dotted line just so it makes more sense when I draw the rest. From that one trace, I'm just going to go ahead and sketch in the picture of the hyperboloid of one sheet. You saw it on that list of formulas, right? It kind of looks like that. And I'm going to go ahead and sketch that in on my picture. Just kind of comes up and out, and down and out on both sides. Technically it goes on forever, but just to kind of finish my picture, I'll sort of show a spot top and bottom, but technically it would keep going up and out and down and out forever. I didn't mention orientation here. This is actually oriented around the z-axis. Notice that the z-axis runs right up through the center, and that was a perfect match for the formula given on the formula sheet. But I can actually make slight changes, and I can take these same shapes and I can orient them around other axes. We'll see this again as we do more examples, but I will say right now, if the x had been negative and the z term had been positive, I would have had the same shape. It just would have been laying sideways and it would have been oriented around the x-axis. Same idea had the y been the negative term, it would have been oriented around the y-axis. So we can orient these things around any of the axes. All right. I'm going to do one more and then we'll take a look at, one more and then we'll take a look at some maple. This next one, I'm going to notice that two of the terms are squared and one of them is not. If you notice on the list of formulas, whenever we have a term that's not squared, the equation is actually solved for the non-squared term. In this case, it happens to be z. In mine, it happens to be x. So I'm going to follow that. I'm going to solve this for the, in this case, the x. So x would be y squared plus z squared, and then they'd both be divisible by, or divided rather, by 4. All right, that is now a pretty darn good match for this, right? The only difference is, instead of z equals, I have an x equals. So I think it is going to be an elliptic paraboloid, but instead of opening around the z-axis, or oriented around the z-axis, Mine is going to be oriented around the x-axis. So elliptic paraboloid oriented around the x-axis. I'm going to pretty much just sketch from there. There were no shifts, so I'm assuming that my vertex would still be here at the origin. And then I'm just going to draw that kind of a bowl-shaped thing, if you will, coming out and opening around the x-axis, like so. All right, let's take a look at both of those graphs in Maple. This is implicit plotting, since I've got graphs not necessarily solved for z, in fact, not solved for z. There we go, there's the first one. So here's I did my with plots, and this is an implicit plot in 3 dimensions. So it's implicit plot 3D. Notice this is my first example. The x squared plus y squared minus 4z squared equals 16. I played around a little bit to set my window, my x, y, and z ranges. Those worked out pretty well. Sometimes you maybe need to play with them a little bit to get the picture that you want. And notice this looks just like, or pretty close to anyway, that hyperboloid of one sheet that we looked at first. Rotate it, kind of look down the center of it there. I think that looks pretty much like what we graphed, so I'm pretty happy with that. By the way, if I center this, so I'm looking right down the z-axis there, right down through the center, and I change my axes to normal. Oops, I need a comma in there. Notice you can really see that trace, that circle of radius 4, right? 1, 2, 3, 4 in each direction. That was the trace in the xy plane. So kind of a nice little connection there that you can see. All right, the next one was that last elliptic paraboloid that we looked at, this one here. I just went ahead and did my x, y, and z all from -10 to 10. And this time, I actually set my style a little bit different. I set my style to surface. So if you don't like all those little grid lines running all over your shape, and you prefer more of a smooth surface, that's what I did here. That's that style equals surface. And I did set my axes to normal, so you can really see that x-axis coming right out of the center of that paraboloid. All right, let's go back and take another look at another couple of examples. These next 2 are going to have shifts in them, so we'll look at both of those first by hand and then by Maple. Let's see. Here, I'm going to notice that I've got an x and a y shift. We have to complete the square to really see what those look like. So I'd have x squared minus 2x, keep those together, plus y squared plus 6y, I'm going to keep those together, plus the 4z squared equals 6. I need to complete the square, so I'm going to add 1 and add 3 squared would be 9. So I'm actually adding a total of 10. Keep it even by adding to the other side as well. And I have x minus 1 squared plus y plus 3 squared plus 4z squared equals 16. Now these are shifts, so we'll talk about those in a minute, but let's identify the basic type of graph we're looking at first. And I actually, oops, that's the wrong one. I actually think we're looking at the very first one here. All the squared terms are positive. This is equal to 1, so I can go ahead and divide everything by 16 here, which I'll do in just a minute to get that 1. But basically, I think I'm looking at an ellipsoid. which will be sort of this egg-shaped thing. So I am going to go ahead and divide everything by 16, both sides. And I have an ellipsoid. As far as the shift, the center is going to be at 1, -3, 0. All right, I'm going to start by more or less locating that. In the xy plane, if I go out x equals 1 and y goes to -3, I'm going to be about here, approximately the center of my ellipse. And then in order to figure out kind of how far to go in each direction, what I'm going to do is I'm going to think in terms of each variable individually. So if I just think about the x's for a moment, if I brought that 16 over here and took the square root, from the center I would be at plus or minus 4. Y is going to work the same way, right? If I pretend I'm not even looking at the x and the y for the, or x and the z for the moment, multiply the 16 over again, square root of both sides, that's going to become plus or minus 4 again. And from the center, the z, that'd be z squared equals 4. So from the z, we'd go plus or minus 2. So I'm going to basically just try and draw that. I'm going to say in the x direction, I'm going 1, 2, 3, 4. And this way, 1, 2, 3, 4, about like that. Oh, excuse me, that was the y direction. In the x direction, I'm coming out about 1, 2, 3, 4. I'm going back about 1, 2, 3, 4. So there would be my elliptical trace in the xy plane. And then the z only goes up 2 and down 2. So up about 2, it's going to come up about here, down about 2, down to about there. And I guess I would actually see this line. So there's my attempt at drawing that ellipse. Maybe we'll go ahead and look at that in Maple right now, because that was a hard one to draw. There's my ellipse. Again, you can see the same equation that we just did. And I said again, my x, y, and z, I played around with those a little bit so I could see the whole ellipse nicely. I do have my axes set to normal and my styles set to surface. I'm actually going to put my scaling over here on constrained so I can really see the correct proportions in the x, y, and z directions. And one other thing, we've played with transparency before. If you want to see where those axes are cutting through your shape, you can just make them slightly transparent. Should be able to anyway. Oh, sorry, I'm not on this one, that's why. There we go. A slight transparency allows you to actually see the axes cutting through and allows you to see where the center would be a little bit better. All right, we got a couple more to go here. The next one also has some shifting going on. So let me go ahead and play with that a little bit first. We'll get the x's together. Oops, that's actually a minus on the y's. I'm going to be a little careful there. I'm subtracting the y squared. So when I put the 4y in here, I'm actually going to put it in as a negative 4y minus the negative would make that the real positive that I had to start with. And then I've got a minus z squared. All right, completing my squares. to add 4 in here, have to add 4 in there. And I think I've actually added 0. Right, that's really a +4, but that's really a -4. So the two things that I've put in cancel one another out, and I don't actually need to add anything to the other side. Just to emphasize it, I'll put +0, but nothing really changed there. All right, so I've got x minus 2 squared, subtract y minus 2 squared, subtract z squared equals 0. All right, I don't have a constant term on this one. And as I'm looking at these, I'm thinking, I think the one I actually want is this one. I'm going to have to rearrange my terms a little bit. Right now I've got a positive and 2 negatives, but if I move those 2 negatives to the other side, it would look a lot more like this, right? A positive on one side and then 2 positive terms on the other side. So I think I have an elliptic cone here. Let me make the changes. I'm going to keep the x minus 2 squared where it is. I'm going to make that y minus 2 squared plus z squared. I'm going to say this is an elliptic cone. It's oriented around the x-axis, and I'm going to have a little more to say about that. Right, and the reason I said it was oriented around the x-axis is because the x term was by itself. Right here, the z term was by itself, and it was oriented around the z-axis. So mine's going to be oriented around the x-axis. But then we also have a shift. The new center is going to be 2, 2, 0. So when I say it's oriented around the x-axis, it's actually going to be oriented around the shifted x-axis, not the true x-axis. All right, let's see what we can do here. 2, 2, 0. X is 2, y is 2. We'd be about here for our center. And in fact, I'm just going to draw a shifted x-axis right in here. And then I want to draw my cone. Center goes right there, the vertex. And there's going to be one piece of the cone coming out this way, and the other piece will go back that way. Cones are actually double cones. So this piece will come out like this. And then there'll be a piece that goes back like that. All right, let's take a look at that one on Maple. It's down here. You can see that indeed I've got sort of that double cone. We'll talk about that gap in there in just a minute. Again, I've played around a little bit with the windows just to kind of make it look good. And I'm going to do one thing here. Oddly, it looks like I don't have a real point, a sharp point on the two pieces of the cone. They don't meet at a vertex, when I know, based on the picture, that they should. What's happening here is Maple's not graphing enough points to see that center point. I can fix that by saying the number of points, or num points. And I'm going to make it a big number. I'm going to go with 50,000. And you can see by doing more points, we now see that vertex that connects the two halves of the cone. All right, we got one more. X squared minus y squared plus 3z equals 0. And we saw before that when one of the variables is not squared, typically if you solve for that variable, it's going to be easiest to find the match. So I'm going to do that. I'm going to say 3z would be minus x squared plus y squared. So z would be minus x squared over 3 plus y squared over 3. All right, that is closest to this very last one, this hyperbolic paraboloid down here. Z equals, now my x and y signs are backwards, so my hyperbolic paraboloid is going to be oriented just a little bit differently, but it should have that same sort of saddle-like look to it when it's finished. You'll see when I draw these, to make them look at, this is the hardest one for me to draw. When I draw it, I'll make a slightly different look to it, but I think it'll be okay. All right, so I think we've got a hyperbolic paraboloid. All right, well, here we go. I'm actually going to use some traces to help me out here. I'm going to say, let's do the xz trace, and then I'm also going to do the yz trace. What that's going to do is actually going to help me with the orientation. So for the xz trace, I'm going to put 0 in for y. So z equals minus x squared over 3. That would be an upside down parabola, right, with a negative there. So for now, I'm going to make everything dotted. I've got that upside down parabola in the xz plane. In the in the yz plane, the yz trace, I'd have z equals y squared over 3. Also a parabola, but this time right side up. So in the yz plane, I have a right side up parabola. All right, here's what I'm going to do. I am going to draw this saddle shape, at least I'm going to try. And I'm going to do that by saying I know that this upside down parabola shape is going to get shifted out here as I go a little bit further. So out here along the y-axis, I'm going to continue to have these sort of upside down parabolas out through the end. And then here I'm going to continue to have the right side up ones. Okay. Now, like I said, these do not look real great when I try to draw them. They're going to look much better on maple. I'm not a real good three-dimensional artist. I guess I should probably put these in. Solid. If I look at this on maple, it's going to look a whole lot better than that. It'll look more saddle-shaped. Here's that one. You can see the upside down parabola, and this way you can see the right side up parabola. And again, much better perspective here than I could draw by hand. So there's that saddle shape in maple. All right. In this section, my main goal is for you to be able to identify the type, orientation, and shift, make at least a credible attempt to sketch, but of course you always have maple to back you up as far as trying to help you out to visualize the sketches, and that's always going to be fine as well.